This is going to be our first look at infinite series of numbers. It's not a topic that we're going to spend that much time with for two reasons. The first is that I think most students work through infinite series in depth in a calculus course. And then also, we will actually be more interested later in a different type of series. In particular, we'll be looking at series of functions where what we're adding up are actually function expressions. However, we do want to define the basic notions of infinite series, and we're going to prove some of those famous tests from calculus together. So we'll prove things like the ratio test, limit comparison test, that sort of thing. And I hope that you will find those exercises fun. Let's look at the definition of an infinite series. I phrased it here in terms of sequences. So in particular, if we have a sequence of terms, so I'll refer to these as terms. Of course, this is an infinite sequence, A1, A2, A3, A4, etc. We can imagine adding up the first n terms to form something we'll call the nth partial sum. So the nth partial sum, S sub n, is the sum of A1 plus A2 plus A3, et cetera, until you get to the nth term that you would be adding up in this finite sum expression. So every partial sum should exist. Every partial sum is just a number that you get by adding up n terms. And we can collect them together using this big sigma notation, where here a sub k represents the terms, starting from, in this case, k equals 1 and going up to the nth term. I say in this case because often the lower index is 1, sometimes it's 0, sometimes it's 2. It doesn't matter so much where you start the series because you're looking at adding up, an infinite number of terms. All right, so we say that a series, an infinite series, where here I'm going to imagine adding up the terms in my sequence forever. So it's like, could I add up all of the terms in my sequence? Converges to some number L, which you could think of as the sum of this infinite addition that you form by doing the infinite series. We converge to the number L if the associated sequence of partial sums converges as a sequence to L. So this is a kind of convergence that we're very familiar with. This is just saying, does a sequence converge? The sequence that you form by taking partial sums. If this sequence converges, then it makes sense to say that this infinite sum converges, and its sum, what it adds up to, is this limit here, the limit of the sequence of partial sums. And then if that sequence does not converge, maybe it grows to infinity or it bounces back and forth between two different numbers or something like that, then we say that the sum doesn't exist or the sum diverges. All right, so now that we've had the definition of an infinite series phrased in terms of looking at the sequence of associated partial sums, we'll just work through a couple basic notions for the rest of this video. Before we take a look at our first example, let me say a little bit more about notation because I think it's easy to accidentally mix up your indices here. It is often the case that series will be indexed with the letter n, and in fact, I did that a moment ago on our first slide. You have to be careful, though, when your series is not starting with a lower index of 1, because you might have a sequence of partial sums that you start with S sub 1, but then your series might start with 2 or 3 or 0. And so you just have to be careful that you're not overusing an index and having it kind of count off differently. So if your series starts at 1, and then your first partial sum is S sub 1, it's okay to use the letter n, but if it starts anywhere else, I recommend indexing series with a k and then indexing your partial sums with n. It's an easy thing to mix up. So here, when I say better, I don't mean it's better to start a series with a lower index of k, but rather be conscientious with how you choose your index. So here it's like, okay, I'm starting with 3, let me pick k, and then my associated sequence of partial sums, I would index with n. That's a choice I make. So you don't have to do exactly my conventions. I just want to alert you that you might have indexing through your series terms and then indexing through your sequence of partial sums. And if you're ever looking at something and it doesn't make sense to you, just keep that in mind that you might be overusing an index. Also, in a proof, I might just write this to indicate just the general idea of an infinite series, acknowledging that it's an infinite series that goes off to infinity, but I don't really care where it starts. Okay, I think I've said enough about notation for now. I will try to keep my notation very clean. I apologize if I do make a mistake along the way. Our first example is the most famous example of a series, and if you can only learn one kind of infinite series of numbers, make it this one, the geometric series. Comes up all the time. It's a very special series. Additionally, it's a very nice series because we actually have a closed form expression for what it adds up to when in fact it does add up. And that's very special. So a lot of series might converge, but we don't have a way of writing down what the sum is. For geometric series, we do. Okay, so how do we form a geometric series? Well, what we do is we take a base, little r, and we just exponentiate it and add those expressions together. So let me actually expand this. If we start with a lower index of 0, go off to infinity, the geometric series that we would form by doing r to the k, the first term is going to be r to the 0, so that's just 1. The second term, you bump this up to k equals 1, is r to the 1, and then r squared, r cubed, etc. Now, often you think of exponentiating as making numbers larger and larger, so it feels like the sum could get very large and not converge. That's certainly the case when r is bigger than 1, say. But what you need to know is that when that base r is strictly between -1 and 1, the series converges, otherwise it diverges. Let's actually, just for practice, write down the sequence of partial sums for, how about 1, -1, and a half? Okay, so partial sums sequence. Going to list them out over here. When r is 1, my first partial sum, s sub 1, is just the first term. My second partial sum is this one, so 1 plus 1. My third partial sum is 1 plus 1 plus 1, the sum of the first 3 terms. And then you see the pattern? So when the base r is 1, we can actually say explicitly that the partial sums forms the sequence that looks like n. To just keep going about notation, notice here that I'm indexing my partial sums with n, so it makes sense to call this n. Here I used k. Okay, so you've got a sequence over here, a series over here. When r is -1, our first partial sum is just 1. The second one is here, 1 minus 1, and then 1 minus 1 plus 1 again, 1 minus 1 plus 1 minus 1. I have seen a video that claimed this converges to a half. That is completely false. That's nonsense. This does not converge. It does not converge. And hopefully at this point in the course, you have several rigorous justifications that you can use to support that this does not converge. For one thing, you could extract a subsequence of all zeros that converges to 0, a subsequence of all ones that converges to 1. Well, if you have two subsequences converging to different limits, the overall sequence does not converge. I can't tell if I'd said sequence every time I meant to here. Sequences and series, it's easy to get the words mixed up. So let me say that again. There's a subsequence of all zeros converging to 0, subsequence of all ones converging to 1. Different subsequences with different limits means the sequence does not converge. Another argument you could make is that this sequence is not Cauchy. So you could write down an argument showing that you can always find a pair of terms beyond any threshold whose pairwise distance between them is 1, which, if you pick epsilon less than 1, it's going to violate the definition of a Cauchy sequence, and since it's not Cauchy, it's not convergent. Okay, so I just wanted to say at this point in the course, you have different ways that you could show that this sequence does not converge. However, if r is a half, we have 1 plus a half, I will write 1.5. 1 plus a half plus a quarter, 1.75. And probably feel what that converges to, or you already know. It's going to converge to 2. So the sequence of partial sums converges to 2, which means that the series we get by plugging r equals 1/2 into this expression converges as well, and we say that its sum is 2. Okay, so I just wanted to practice going back and forth between the idea of a series and the idea of its associated sequence of partial sums. All right, so how do you know that this converges to 2? There's this formula that we will prove in a moment. If you are starting with a lower index of 0 and your base is between -1 and 1, then the associated geometric series adds up to 1 divided by 1 minus r. Don't memorize that, memorize this, regardless of the lower index. So here I'm saying k equals j could be 0, could be 1, could be 4, could be 10, doesn't matter. The geometric sum adds up to first term divided by 1 minus r. This is a special case of this one. So this is all you need. For geometric series, always say first term divided by 1 minus r. You've probably seen geometric series before, so I assume that this is familiar to you, but what we are going to do now is prove, I think we'll prove this one and then get this one from that. Okay, so let's focus on writing a good proof. We will prove the first formula first, where we have the lower index of 0. As we already saw, when r equals 1, the associated sequence of partial sums is just 1, 2, 3, 4, 5, 6, 7 that goes to infinity. So that does not converge, which means that from now on, if we say r is not 1. And I just need to make that precise first because in a moment we're going to arrive at this fraction and I don't want the denominator to be 0. So that's why I'm isolating that first case. All right, so now imagine that r is not 1. And what does a partial sum for the series look like? Well, the nth partial sum is the sum of the first n terms, starting with r to the 0, then r to the 1, all the way through r to the n minus 1. We are going to show first that this finite sum, the sum of the first n terms, adds up to 1 minus r to the n divided by 1 minus r. You don't need to write anything down yet, but just to kind of check your proof instincts, I would like for you to propose a method of proof for this conjecture. So, if you were faced with doing this, how would you attempt to show it? I am not about to do a proof by induction, but that's what I wanted you to have the opportunity to come to. And that is anytime you see a formula like this, where the formula is created by choosing some finite natural number n, it's a natural context for induction. And you could certainly prove this with induction. So I just wanted you to have that kind of reaction to seeing this formula. We're actually going to do something that feels a little bit clever and like a trick. So again, you could do induction, it's perfectly valid, but there's a faster way. So notice, let me just rewrite my partial sum expression here. And then what I'm going to do, let me just do it directly to this line, is multiply both sides by r. All right, so on the left-hand side, we have r times Sn. On the right, what I'm going to do is distribute. Let me bring in here what I would have called r to the n minus 2. In fact, just to make it super clear, let me add that. Okay, so okay, but now if you look at this, should look familiar, right? It's almost exactly what we started with, but we're missing the 1. So what I have here is what I have here in terms of matching the terms. So in particular, we could take this expression and replace it with s sub n minus 1. Right, so if I had a 1 here, it would be exactly what we started with, but I'm missing that 1. So that's why I did s sub n minus 1. And then we still have this term left over. Let's isolate s sub n. So I'm going to collect this over on the left-hand side. We have a total of r minus 1 copies of s sub n equals negative, let me write r to the n minus 1. Divide both sides by r minus 1. This is the same thing, but let me just multiply top and bottom by negative 1. And when we do that, we can rewrite this expression as 1 minus r to the n over 1 minus r. All right, so there, we could have done it by induction, but I just think this trick is kind of nice. Taking this expression and multiplying both sides by r works out very nicely. And now we're really almost done, because if you look at this, if r is between -1 and 1, r to the n is going to go to 0. So this is going to go to the right place. We'll write that down formally in just a moment, but you can see hopefully that we are very nearly there. To wrap this up, a few different times we've talked about what happens to numbers between -1 and 1 when they are exponentiated. So let me just say from before, if -1 is less than r is less than 1, r to the n goes to 0 as n goes to infinity, which is good because we can say that consequently Sn goes to 1 over 1 minus r as n goes to infinity. Thus, for all r strictly between -1 and 1, the geometric series starting with a lower index of 0 for this first case adds up, and it adds up to 1 over 1 minus r. Now we need to address the case that the absolute value of r is greater than or equal to 1. I mean, we've already looked at r equals 1 and r equals -1 individually, but let's just do all of this at once. You might start saying, okay, well, if r is bigger than 1, r to the n blows up. If it's less than 1, or it's less than -1, so it's negative, we kind of have different behaviors happening there. Should we do it by cases? It's actually much easier than even looking at this formula. And I want to do it this way to kind of lead into the next video. We're going to kind of pick up with some of the ideas from the following argument. Let's just look at the difference between consecutive partial sums. Choose any natural number, little n, and notice what's the difference between the partial sum s sub n plus 1 and s sub n. Well, this partial sum has all of these terms plus a final one, r to the n. Maybe I'll write that out. I'm getting confused here with my indexing. So s sub n ends with r to the n minus 1. So this one should end with r to the n. There we go. Minus, and then this one is 1 plus r to the n minus 1. Okay. Basically, they differ in this term. That's what I'm trying to get to. We can write that as the absolute value of r to the n. Okay, everything else cancels out. And then the absolute value of r is a number greater than or equal to 1. So this expression is greater than or equal to 1 to the n, or just 1. What I want to point out here is that that means that the sequence of partial sums as a sequence cannot possibly be Cauchy. If adjacent sequence terms are at least 1 unit apart, then if you pick epsilon equal to a half, there is no threshold beyond which any two terms will have a pairwise distance to each other less than epsilon, because you can always just take any pair of consecutive terms beyond any possible threshold, and the distance between them is at least 1 greater than epsilon. Okay. I just wanted to take this very sequential point of view because we're going to talk about the Cauchy criterion for series in the next video. So let me just say, so S sub n is not Cauchy. And if you are not Cauchy, then you are not convergent. All right, so I wanted to do kind of a sequential theme proof here, because again, we are thinking about convergence of series by looking at the convergence of their sequence of partial sums. So here we're talking about S sub n as a sequence. That's not a Cauchy sequence, so it's not a convergent sequence. That wraps up this look at geometric series. Again, this formula right here is one of the most famous in mathematics. Actually, we haven't wrapped it up yet because I want to take this and get to the one I said is really what you should keep in mind, that first term divided by 1 minus r. So let me erase this. In just a moment, we will build off of this expression in order to get that more general expression. All right, this computation is very fast. Let me set it up in case you don't immediately see how to do it, but I would like for you to work through to the end. We can take this expression here. So the idea is we are starting at some random lower index j. We can think of this as the geometric series starting at 0 and taking off the first j minus 1 terms. So that would be like from k equals 0 to j minus 1. I'm sorry, this should be k. And so should this. Hang on a second. Again, as I said a few minutes ago, when you work with series, there can be a lot of indices, and anytime something doesn't look right, check your indices. Okay, I think these look right. So this is the entire geometric series, and then we want to take off the first j minus, or up to j minus 1, so that we ultimately preserve from r to the j off to infinity. See what you make of this right-hand side. Using the two formulas that we just proved, this first expression is just our basic formula, 1 divided by 1 minus r. And then this one, we can use that intermediary formula that we proved. So this is a finite sum. We're stopping when we reach r to the j minus 1. If you look at the formula we proved, it was that 1 plus r squared all the way through r to the n minus 1 was equal to 1 minus r to the n divided by 1 minus r. Here, if we write this out, we're starting with 1, then r squared. We're stopping at j minus 1. So this should add up to 1 minus r to the j divided by 1 minus r. We have a common denominator, so we can go ahead and say 1 minus 1 is 0, minus negative r to the j leaves us with r to the j divided by 1 minus r, which is exactly what we wanted to see. And again, I like this expression because if you can just remember first term divided by 1 minus r, you're covered whether your geometric series starts at 0 or 1 or 2, whatever it is. All right, I think we should wrap up this first look at series here. In the next video, I just want to work through the proof that the harmonic series diverges.